Hi, welcome to A101CEC, Electrical Engineering 1. Once again, this is your lecturer John, and this time we'll be discussing about capacitors and inductors. Last time, we have discussed about resistors. Now, we'll be discussing about the two other elements in electrical engineering, which are capacitors and inductors. What is a capacitor? A capacitor is a passive element. It is capable of storing energy in its electric field. A capacitor basically consists of two conducting plates which are separated by an insulator, which is normally called a dielectric. How does a capacitor store energy? When a source is applied across the two plates, the positive side of the battery delivers positive charge in one plate, and the negative charge of the battery delivers negative charge on another plate. The charges on both plates should be equal in magnitude. We can say that the charge on the plate of the capacitor is proportional to the applied voltage. This proportionality constant can be said to be the capacitance of the capacitor. Thus, we can say that the charge in a capacitor is equal to its capacitance multiplied by the applied voltage. The unit of capacitance is farad, but farad is a huge quantity. That is why most capacitors are measured either in microfarad, nanofarad, or picofarad. The capacitance of a capacitor is determined by the geometry of the plates. The capacitance is proportional to the area of the plates and inversely proportional to the distance between them, which means that the larger the area of the plate, the larger will be the capacitance. And the farther the two plates are separated, the smaller will be the capacitance. The types of capacitors are determined by the type of dielectric being used. Thus, we have mica capacitors, polyester capacitors, or electrolytic capacitors. Capacitors can be also variable. They are varied by changing the distance between the two plates. But how do you use the capacitors? Capacitors have a wide range of applications. They are commonly used in blocking DC signals in circuits while allowing AC signals to pass through. Capacitors are also used as phase shifters. They are also able to store energy and are also used in filters. Current only flows in a capacitor if the voltage across the capacitor changes. That is the reason why it is able to block DC signals, because in DC, the voltage is constant. Thus, there is no current flowing through the capacitor. Whereas in AC, the voltage is changing. It is constantly changing. Thus, current flows through the capacitor at AC. When we discuss resistors, we talk about series and parallel connections. We can have the same in capacitors. When we connect capacitors in parallel, in effect, we are actually increasing the surface area of the plates. So again, what happens when the surface area increases? The capacitance increases. That is why when you connect several capacitors in parallel, the total capacitance should increase. Therefore, if you want to find out the total capacitance of several capacitors in parallel, you just simply add the individual capacitances. Thus, If we have three capacitors in parallel, the total capacitance should be C1 plus C2 plus C3, where C1, C2, and C3 are the capacitances of capacitors 1, 2, and 3. So what happens when you connect several capacitors in series? When you connect several capacitors in series, you effectively increase the separation between the plates. When the separation increases, the capacitance decreases. Therefore, if you have series capacitors, the total capacitance effectively decreases. Thus, if we have capacitors C1, C2, and C3 connected in series, the total capacitance CT can be calculated as 1 over CT is equal to 1 over C1 plus 1 over C2 plus 1 over C3. Let us now go to inductors. Inductors are another type of passive element. An inductor stores energy in its magnetic field. That is how it differentiates from capacitor, wherein the capacitor stores in the electric field. Any conductor essentially has an inductance, but we can enhance the effect by forming a coil from the conductor. That is the reason why the symbol of an inductor is a coil of wire. We can find different applications of the inductance in power supplies, in transformers, in filtered circuits like a capacitor. In DC, the voltage across the inductor is zero. Why? Because current flows freely in the inductor. Voltage will only be developed across an inductor if current is changing. That is why voltage is only developed across an inductor in AC. Because in AC, we can say that current is alternating from positive to negative. It is constantly changing. Thus, voltage can be developed across an inductor. We can say then that the voltage across an inductor is equal to the inductance L multiplied by the change in current per unit time. The inductance of an inductor is dependent on the number of turns of wire around a core, as well as the cross-sectional area of the core and the length. The material used for the core is defined by its magnetic property called permeability. Permeability is the characteristic of a material to freely allow the flow of magnetic circuits. Let us now extend series parallel combinations to inductors. Let us start with series combinations. Assuming we have several inductors in series, each inductor will have a different voltage developed across it. Let us say the voltage developed across each inductors will be V1, V2, V3 up to Vn. Since they are connected in series, we can now then apply Kirchhoff's voltage law or KVL to the circuit. The total voltage V will then be equal to the sum of the voltage across each inductor, which means that V is equal to V1 plus V2 plus V3 plus V4 up to Vn. Since the current through each inductors will be the same, we can then factor out the current from the voltage equation, and we can then say that if we have several inductors in series, the total inductance will be the sum of the individual inductance, which means that the total inductance L will be equal to L1 plus L2 plus L3 plus L4 up to Ln. Note that inductors have the same behavior as resistors. How about if we have parallel inductors? If we have parallel inductors, we can apply Kirchhoff's current law or KCL to the circuit, which means that the total current flowing in the circuit will be the summation of current flowing through each inductor. Means that total current I is equal to I1 plus I2 plus I3 plus I4. Putting this current into the current voltage relationship and factoring out currents and voltages, will be coming up with the equivalent inductance. Note that the parallel combination will then resemble that of the resistors. We can then say that, assuming that we have three inductors in parallel, L1, L2, and L3, the total equivalent inductance LT can be calculated as 1 over LT is equal to 1 over L1 plus 1 over L2 plus 1 over L3. Thank you and have a great day. Remember, work hard, work smart, and work your way to your dreams.